Welcome to AP Podcast 14.4. This is about calculating the pH of solutions. Now what we're going to do is we're going to take the awesome knowledge of pH that we've acquired over the last podcast and we're going to apply it to solutions, which is going to make it a much more practical situation. Now there are a few things you want to remember when you're doing these problems, things to make it easy. Look at this first bullet. Always write down the major ions in solution. So if I'm dealing with an acid, I want to write down H+, maybe I want to write down the anion. Well, I know maybe about that. Don't forget there's water involved. Maybe there's some OH involved. But what you want to do is write out the ions, just like when we do problems, we typically write out a balanced equation. That way, it's sometimes easier for us to get the visual and make sure we don't make some of those silly mistakes we tend to do. Here's another thing. Remember that these are equilibrium problems, right? And so you've done enough equilibrium problems to where you've got the skills to solve them, but don't forget that they are equilibrium problems and that might play a role into how you solve them. And then this is the last one right here. Remember the chemistry. Oh my goodness. Don't forget, you know a lot of chemistry at this point. You know a lot of different types of reactions, whether it's double replacement or some kind of precipitate reactions or some kind of combustion reactions. You know, we're dealing with aqueous reactions here. But don't forget the chemistry. You know what's going on. Pay attention to that. It'll make the problems easier. And then this last one right here, don't try and memorize. There's no one way to do this. Read page 655. It's very important. And you're going, what? 655? Well, I've got that page right here. And I would recommend taking a moment and reading this page at home because I'm just going to go over it quickly. But there's a few really, really good important points on this page. Now, it is very typical for students to want to learn how to do problems, memorize how to do them, and go over and over and over. And one of the toughest challenges you're going to face with acid-base chemistry, and more specifically acid-base equilibrium problems, is there's so many different ways to do them. You've just got to really think about the chemistry, and that's what this, you'll hear me say think chemistry all the time. All right? Well, I didn't make that up. I just got this from our book. You've got to really think about what's going on because you're going to find over and over and over that the same kind of problems are going to pop up, but they can throw in something different. And if you're not thinking about the chemistry, you get in that habit of doing the problems the same way, and all of a sudden you find yourself doing something wrong. All right? Be systematic. All right, acid-base or step-by-step problems, we're going to go over those. We're going to do a lot of them. Be flexible, all right? What happens is that you've got to remember every single problem is different. I know we're going to do some that are similar, but you got to be flexible with it. The be patient part has to do with the fact that some of these problems you're going to read them and you're going to go, huh? Well, you hear me do that in class a lot. Hey, all we do, take a moment, write out reaction, list what we want to, what we have, find some moles, and we can go from there. And then I like this part last year, be confident, right? That's what we're trying to build. We're trying to build confidence. And it's my hope that by the time we're done doing all these problems, you'll be confident about this. And then I like this last little part that's super important. And you'll, hear me say this a lot. You guys know that in my room I've got this up on the wall. Think. You've got to think about what's going on. I can't emphasize this last little bit. Don't just memorize. Oh my gosh, people want to memorize how to do equations and how to do all this. This is beyond that. This is where it really gets tough, and you've got to really think about what is going on. So with that little bit of those few words of wisdom, let's move on to some solution calculations, all right? Here we go. We'll start with the easiest, strong acids. Now, why in the world is that easy? Well, because you guys know that strong acids are strong because they are completely dissociated, right? You don't have to worry about what percentage is going to break up, is it going to be dissociated or not. You know that whatever the concentration of your acid, all right, whether it's a 0.1 molar, 0.5 molar, that is the concentration of your H+, all right? And so that's important. And it also makes the problems very easy if you're paying attention. And then remember this whole Kw, right? Kw equals 1 times 10 to the minus 14th. Since H is going to be a big number, because we're dealing with a strong acid, you can imagine that the OH concentration is going to be a small number. But again, you just got to really visualize and think about what's going on. And then at this very bottom bullet right here, this is something that happens once in a while. If the concentration of the acid is less than 10 to the minus 7th, the water contributes the H plus ion. I can tell you this, they will throw a problem in every once in a while that does that, and it's kind of silly, but again, when you're thinking about chemistry and you're trying to rationalize all these problems, it will make a little sense if you pay attention to those numbers. So let's try one problem and see how you do. All right, look at this. We've got a solution. It's prepared by mixing 90 mils of HCl and 30 mils of HNO3. Water's added until the final volume is 1 liter. Calculate the H plus, OH, and pH of this solution. So the first thing I'm going to do is write out my major species here, right? I've got some HCl. So what does that give me? That gives me some H plus, some Cl minus, all right. I've got some HNO3, that gives me some H plus, and some NO3 minus, right? Now, water is also an issue. Water's floating around, but you guys know the autoionization of water, 1 times 10 to the minus 7th. I mean, it's just, the concentration for H from that. And it's not even going to be a factor, right? So water's not a factor, and typically it's not going to be a factor. NO3, it's the anion of a strong acid, not a factor. Chloride, the anion of a strong acid, not a factor. So I really have some H plus floating around, and I've got to find the number of moles, right? So look what they've given us. They've given us a volume. They've given us a molarity. Well, we're so good at this by now, we can find moles, right? So 0.09 liters times 5.00 moles per liter, right? That's going to give me 0.45 moles. All right, there's that one. Now for the oops, let me write my H plus there. Now for my nitric acid, I've got 0.03 liters, and the molarity there is 8.00 moles per 1 liter, and that's going to give me 0.24 moles of H plus. All right, now I've got to find the concentration of those two things plus the pH. Well, as you know, I've got moles here. Let's find my total moles, because again, it's floating around in the whole beaker. So that would be 6.9 moles. And then what kind of volume am I dealing with? Let's see. Water is added till the final volume is 1 liter. So that makes it fairly straightforward. It's 1 liter. Okay. So my molarity is 0.69 molar, right? Okay. So now that I know that, I know the concentration of H. What's the pH of that? Well, I'm going to take the negative log of 0.69, and let's see what that gives me. According to my calculator, the pH equals 0.16. Okay, so I've got my concentration of H plus, I've got my concentration of, or my pH is 0.16. Now I still need my OH concentration. And so I know the OH concentration equals 1 times 10 to the minus 14th divided by my 0.69, and that's going to equal 1.44 times 10 to the minus 14th. Which is really small, right? And that's what we would expect, because why? Well, if I go back to the slide, we're dealing with a strong acid, and we know that the OH is going to be small because of this equilibrium, right? So hopefully that makes sense. We do these same types of problems anytime you see a strong acid, and you'll appreciate a problem that's a strong acid, because trust me, when we start doing with weak acids and weak bases, and it gets really messy. So anyways, like always, see you next time. If you have questions, we'll talk about it in class tomorrow.